All right, so let's talk about limits involving infinities. All right, so let's go ahead and do this. So limit involving infinity. So we can make if we can make values of f of x arbitrarily large as they become sufficiently close to a number on either side but not equal to a, we write this. So here we say the limit of a approaches increases without bound, but we really just say the limit of a approaches infinity, right? That's really what we say. Technically, we should say the limit increases without bound as x approaches a. But this is what we usually say. F of x becomes infinite as x approaches a. And so, or another notation is f of x will go to infinity as x goes to a. Notice that when we write this, the limit does not exist, right? And so technically it doesn't exist. Now, what does your book do? It says find the limit. I'm like, well, you can't say that and then do that, but it does. It's fine. And I get why it does. It technically doesn't exist, but because infinity is just, it's more of notation. And so we just do it. And so it's just a big little caveat. It's like, hi, it's not really what we're saying we're doing, but we're just going to do it anyways. And so let's do this. So let's calculate something and try to find the limit as x approaches 3 of the graph and given this. And what happens as x approaches 3? So let's just crunch through some numbers real quick. Let's crunch through some numbers. And so here, if I crunch through this number, if I pre-crunch through the number, so I'm not going to slowly type them in with you. I'll just tell you what the answers are, right? So here, notice here I can probably get you to the answer really fast by hand. So notice here that this is 1 over, if I put in 2.9, this becomes 0.1 squared, and so this would be 0.01. So if I flip it over, it becomes 100. Notice if I put in 2.99, this becomes 0.01. And if I double that, it'll be 0.0001. And if I flip that over, it becomes 10,000. Okay. And then here, same thing, this becomes 1 million. And the same thing would happen here. Notice this will be negative when I did it for 2.9. It'll be positive when I do it for 3.1, but I'm squaring it. So this becomes 100. This becomes 10,000. This becomes 1 million. So what happens here? Well, as I get arbitrarily close to 3, right? As I get arbitrarily close to 3, this number gets bigger and bigger and bigger and bigger. So what happens as the values that go to 3? Well, it goes to infinity, right? It goes to infinity and beyond, right? No, just kidding. Got a little Buzz Lightyear flying away. I know somebody at some point will have that on their notes. I've seen strange notes. And so here, what we would say in this case is what we would write in this case. The limit as x approaches 3 of f of x is equal to infinity. Now, this is not technically saying this exists, but we just write it as if it did, right? And so that's what we do. All right, so I'll let you guys write that down. All right, let's go to the next page. All right, so here, if we make values of f of x arbitrarily large and negative, we say it's as x is a close number, but not equal to. We write f approaches decreases without bounds approaches a, or we write it approaches negative infinity, right? Again, also we can say this, but it does not mean the limit exists here. It's just be very careful about that. Now, does it matter? Have I beaten this horse to death? I suppose so. So we'll kind of ignore it from now on. So let's look at this one. Let's look at this one. Can we say, here if we have this graph, right? Can we say that the limit as x approaches to 3 equal infinity? Can we say this? Yes or no? I have one vote for yes, one vote for no, one vote for maybe. It cannot equal infinity. Okay, so what's going on here? So let's look at this in a little bit more detail. Let's do it from the right side. So it's the limit of x approaches 3 from the right-hand side of g of x. This certainly looks like it's going to infinity, right? Because here I just get larger and larger and larger numbers here. But if I notice, if I take the limit as x approaches 3 from the left-hand side of g of x, I get minus infinity, because here it gets smaller and smaller and smaller and smaller. And so can we say that this limit equals infinity? In this case, it's no, right? And the fact is, we could write this, and that's perfectly fine, right? The limit as I approach from the left-hand side is negative infinity, approaches negative infinity. Yeah, I can say that, right? Even though technically it doesn't exist. But here we cannot, because these two are not in agreement of each other. So even in this case, we'll say no, and we'll actually write the limit here. Even with allowing infinities, we'll still write the limit here of g of x does not exist. Right? So we'll still write does not exist. And the reason we write it doesn't exist is because this side of the limit does not equal that side of the limit. Okay. But let's ask us another question real quick. What happens to values of g of x as x becomes infinite? So what happens when I get really far out here, right? What's happening to the values of g of x? As x gets really, really big or really, really small, what values am I getting? Well, as x goes to infinity, right? G of x is approaching what number? What number as I get really large? 0? Two, right? It's getting real close to 2. And so we're going to start calling these things. So we're still going to start labeling these things. So a line. So we're going to start calling this right here, this dotted red line. We're going to call this dotted red line. In fact, I should write it in red since I have the ability to write colors. We're going to call this a vertical asymptote, right? Asymptote. Okay. And here in this light blue, actually make this a little bit lighter in blue. Just hold on. I can get that color. There we go. We call this a horizontal asymptote. Horizontal. Fine, there we go, good enough. Go back to the blue. And so here, as long as any of these, at least one of the following statements are true, we say x equal a is a vertical asymptote. So here, as long as if the limit goes from to positive infinity or negative infinity, or even if just the right side, or here the right side goes to positive or negative infinity, or just the left side goes to positive negative infinity, we say x equal a is a vertical asymptote. So the vertical asymptote in this case, in red, let's go ahead and do red, is x is equal to 3. This is a vertical asymptote. Okay. Then here, in this case, we'll do the same thing here. It's just on the next page. We'll say this asymptote is y equals 2 is a horizontal asymptote. Okay. So let you write that down. And we'll go to the next page. All right, so let's go ahead and go to the next page here. All right, so here we're going to define the other thing we started to play with a little bit. So if a function is defined from some interval all the way to infinity, we can make an arbitrarily close, and it becomes arbitrarily close to L. So here we're, I guess that's fine. I can use the light blue for a little bit. So here, instead of taking values of finite values where the function blows up, we're going to just send x off to infinity, right? And so the limit of f of x as x approaches infinity is L. Okay, so here we're saying this limit. Or as the function goes to L as x goes to infinity. And so here, not only can we have infinites in the function values, but we can also have infinites in our input values. So what happens when we get sufficiently large or sufficiently negative? And this is just the same thing, just for going in the negative direction. As approaches negative infinity is L. And we write this in notation. And this comes up. And we call these horizontal asymptotes. Oops, there should be a little space right there. And so we call these horizontal asymptotes. So let's look at two things as it goes to infinity. Oops, I guess I don't need that there. I want my blue back. All right, so what happens here? So here, I want to find this limit. So as x approaches infinity, right? So as x approaches infinity, 5 over x, so I can rewrite this as this over this, right? However, does this really help us? Not really. But one thing I can do, I don't know if this will help us that much more. Let's look at it graphically. Let's look at it graphically before we do it algebraically. I'm going to show you graphically first. Our notes have different nodes. Yes, I remember I said that I took out the logs. Oh, sorry. I should have mentioned that. This is where I took out the log of x, because your book hasn't dealt with logs yet and that much in your homework or anything, so I got rid of them. It should be live. If you downloaded your notes before I swapped it, you wouldn't know the difference. It's just, I would have told you guys, but it's literally just, it's literally, I just switched the two. I switched ln of x for like x cubed, and I switched this. So if yours look a little different, just quickly fix what it is. Okay. So yeah, just switch out the numbers. Just cross it out and write the right numbers. Your book wasn't dealing with logs yet, and I was like, well, let's just not broach it if your book's not going to, right? When I swap it out, I printed it out. I don't know. It was sometime today. Yes, I was reviewing for the class before I teach it, and I was like, I don't like this, and so I swapped it out. So let's look at this real quick. Let's look at this. Let's look at it graphically. All right, so 5 goes x squared. So notice here, we do have the limit as x goes to 0 would be infinity. But notice here, as we get sufficiently large, what's happening here? Well, this number is overtaking, right? X squared is overtaking. And as that goes to infinity, as I take this to infinity, this goes to 0, right? And so here we say this limit is equal to 0. In fact, anything of 1 over x to the any power, let me be very clear about this. Any power as the limit as x goes to, let me see if I can write this correctly. Any constant over x to the n, to any n, right? Limit as x goes to infinity or negative infinity is always going to be 0. And the reason is that no matter how big this constant is, this number is going to get larger and larger and larger. And so it's going to divide out more and more and more, and this always becomes 0. Okay. And this is like a theorem in your book. I'm like, I don't know if that's necessarily qualifies as a theorem. I think they strictly write it as 1 over x. Let me double check in your book. Hold on, let me double check your book. I want to see what your book wrote. No, I forgot. Book. Where's your book at? Classes, this class, Albuco. Ah, here we go. How's your book writing? You just don't get confused later. I'll be in this section. Yeah. This is how your book writes it. So your book gets rid of the C. It's not necessary. So it says this equal to 0, or so the limit as x to the this is equal to 0, and then here the limit as x approaches minus infinity of 1 over x to the n. It's also 0. Okay. In the way your book doesn't actually split it apart, it actually just does it graphically and just shows you as it goes to 0. So here are 2 things to use. So here you can use this to zero out parts, and we'll use that to solve problems next time. I think we just barely have time to solve this, and we'll get out today on time. So what happens here of x cubed if I go to minus infinity? Well, x cubed over 3. Well, it still looks like, let's look at it graphically. Let's look at it graphically, and then we can do it numerically. And then I'll show you, and I'll make one other statement real quick. So let's look at it graphically. So let's flip this around. X cubed, and divide that by 3. All right. Woohoo. So it looks like x cubed still, right? But notice, as I go closer and closer to minus infinity, this number is just going to get more and more negative. In fact, I don't think I can ever really win because of how negative it gets, right? And so it goes something like this, but it just, so this equals minus infinity because it really just decreases without bound. And so what you have here is, if you have x, the limit as x approaches infinity of x to the n is equal to infinity, right? And then the limit of x approaches to minus infinity of x to the n equals either infinity if n is even, or minus infinity if n is odd. And so here our n is odd, so this would be minus infinity. Okay, and so between this rule, and these, you can solve a lot of things where x goes to infinity, because you either zero out an x or you take x to infinity and it explodes. Now, there are going to be cases where you can't solve things, like you'll have 0 over infinity, infinity over 0. Yeah, we'll deal with those much later. Okay, so let's go ahead and close. Hold on, where's my star? There we go, let's put a little star. All right. So these don't exist, but we're just going to use the appropriate symbol. So here, we're going to look at this one. So the limit. So let's just try plugging it straight in, right? So let's just do the limit. And the first thing you always want to try with the limit is just see if you can plug it right in. And so in this case, we're going to just try. So we're going to try to plug in directly. And so if we try to plug this in directly, we're going to get 4 minus 4, which gives us the limit. So 4 minus 4, which implies, oops, oh, that is definitely not what I want to do. Which implies 5 over 0, right? Well, 5 over 0 tells me this is going to go to infinity, right? So if you have any number over 0, I mean, it's going to tell you it goes to infinity, right? So this limit implies, if I just by plugging it in, it goes to 0. But the question is it positive or minus? So here we're going to be approaching from, we're approaching this from the left side. So we're coming in from the left. And so here, you're going to have values slightly smaller. So here, if I just attempt something, right? So is it positive or negative, right? Is it positive or negative? Let me actually write that out a little bit better for you guys. So here, is it positive or negative infinity? So it says it goes to infinity, but I don't really know what sign it is. So to do that, we're just going to plug in numbers that are slightly smaller than 4. So here I have 3.9 minus 4. Well, that gives me 5 over minus 0.1, which gives me minus 50. So that's telling me that this is going to go to the negative direction. And so overall, we write minus infinity. And we can always double check this with a graph. And so let me open up Desmos. All right, and so here I'll show Desmos. And so we have 5 divided by x minus 4. And notice here at 4, it goes down to infinity. And so that matches what we did here. So usually what happens is if you get some number, over 0, that means that limit's going to go to an infinity, right? Now, to figure out what the sign is, you just plug in which direction you're heading. So let's do this again. Let's do this again for 6, or for b. So here, I'm going to go to -2. So once again, we're going to try plugging it in directly. So we're going to try directly. So here I get the limit as x approaches -2 from the positive side of 6 over -2 plus 2. Well, that implies 6 over 0. So this is going to also go to infinity. But now I want to figure out what's the sign on this, right? Well, here I'm going to be slightly higher than this. And so something slightly higher in this case. So is it positive or negative? So here we're going to just choose, here we're going from the positive side. And so this will be 1.9 or negative 1.9. Negative 1.9 is more positive than -2 plus 2. Well, this equals 6 over 0.1, and that is equal to 60. So this tells me I'm going to the positive infinity, right? And so here I write positive infinity. Hold on, let me shut my door real quick. There we go. And we can double check this in Desmos. So here I have 6 divided by x plus 2. And here at -2, here we notice when we're coming on the positive side, we're going to positive infinity. All right, so let's do this again for C. So here once again, we're going to try plugging it in. And so here we get the limit as x approaches 5 of -6 over 5 minus 5 squared. Well, this is -6 to 0, so that also tells me it's going to infinity. But notice here, I don't have either positive or negative, but it doesn't matter because no matter what this is, if I take any number here that this isn't really 0, but it's like 0, right? This is why I say implies. This is going to be positive. So I'm going to have a negative over a positive. And so I know the sign here is negative because here I have negative over something squared. This has to be positive. And so overall, this has to be negative. And so here I'm going to get minus infinity. Okay. And once again, we can plug that into a graph and check that out. So for all these things where I'm approaching, where I'm kind of like dividing by a 0, it's going to force these things to go to infinity, right? Now, the sign on that, you just say, well, for here, we're just looking at the direction, right? And then here, this has to be positive, right? Anything squared is positive because it was negative, it becomes positive. When it was positive, it stays positive. So I have a negative number over a positive number, so this has to be negative. And so this goes to negative infinity, and we'll just double check this in Desmos. This was what? minus 6. And here we're going to have the quantity squared. And I need a minus 5 here. And notice here we get exactly what we think. Here at 5, it shoots down to negative infinity. Okay. All right. So that's how you kind of handle these for infinity. Now let's take x and send it to infinity. And here we're just going to start with a boring polynomial. So here we're going to start with a very boring polynomial. We're going to send this to negative infinity. Well, what happens here? Well, let's actually just let's just try plugging it in. And that's how you solve a couple of these, is you just try to plug it in. If it doesn't work, you do some algebra, right? But let's just try plugging it in. So try plugging it in. And so what we get here is we get, if I plug that in, I get infinity squared minus 7 infinity. Oh, no, this is minus infinity. Hold on. Let me fix this. Minus infinity squared minus 7 times minus infinity minus 8. Well, what does this end up being? Well, infinity squared is just going to be a positive infinity. Doesn't matter about the 5. And then negative 7 times the negative infinity because it's a positive infinity. So positive infinity plus positive infinity probably equals positive infinity. So how do you deal with this? And so let me show you some things in Desmos. We're just going to play in Desmos for 5 seconds for this. And we're just going to look at end behavior, right? Because that's what we're not really sending stuff to infinity. We're just looking at end behavior. So let me zoom way out. Way out. There we go. So we zoomed way out. So here, if I have x cubed minus 4x, maybe I shouldn't have zoomed so far out. Squared plus x minus 4. Okay, so notice as numbers get larger and larger, whatever is the highest power will dominate, right? It will dominate, even if this is minus 4,000, right? Here at the minus 4,000, it looks like it's completely winning. I may have to zoom out, but notice here, all of a sudden it just changes and it goes whoosh, and zooms up, right? Let me lessen it a little bit, right? So it doesn't matter how big that number is, eventually the highest power wins. And so in order to solve this, so if I take, and so here's just a couple of rules of thumb, right? So you look at the highest power. You look at the highest power. If it's x of x to the n, if n is odd, as x approaches minus infinity, your function's going to go to minus infinity. And if x approaches infinity, your function's going to go to positive infinity. Okay. Now, if n is even, here's x goes to infinity, or minus infinity. Your function's going to go to positive infinity. And as x goes to positive infinity, let me clear this up, make this clear for you guys. F of x will go to also positive infinity. Okay. So it's just like the end behavior. But notice that's assuming there's nothing here. That's just, but let's pretend real quick if I had a minus 4x squared, right? This negative would switch these signs, okay? Because then you switch the signs on these because you need to multiply by this minus sign here. Does that make sense why? For the minus sign, that's your largest power. I was trying to find this limit as x approaches infinity. This would be equal to minus infinity because this would be positive, but this would be negative. Does that make sense, guys? Yes, no, maybe? Nope, all quiet on the chat front. Yes, okay, thank you. All right, so I'm going to take a quick break because you finished writing this down. So the only one where x, so only, yes. That's assuming you have a positive sign, right? That's assuming you have a positive sign. If you have a negative sign, just switch all of these, okay? This only works for polynomials, yes, just for the polynomials. Oh, look for the highest power. Basically, I should say look for your leading term on your polynomial. That's probably, look at the leading term. If n is positive, or if your power is odd, you have these. If it's n's even, and if you have a negative, if it's positive, it's these. If it's negative, swap the signs, okay? Oh yeah, so let me just show you in Desmos real quick exactly what's going on. So let's just do this real quick. So let's look at minus 4x squared. X squared. So notice here, let's just put plus 3x plus 1. Let's just look at this real quick. So here, it doesn't really matter. We just look at the leading term, whatever's the highest here. If it's positive, as x goes to minus infinity, or as x gets more and more this way, this is going to win. This is going to be positive, and this is positive. But if my leading term is negative, as I go from negative infinity to negative infinity for even numbers, it's also going to be that. And that's fine. It's same true, even if I make it 20, it's the same, right? It may look a little bit funny, but it's still going to go negative, negative, and then I'm going at positive 5, it's positive, positive. Now, if this is odd, let's go ahead and make this 3 just for ease of seeing. It goes to negative infinity as I go to x goes to negative infinity, and positive infinity as x goes to positive infinity. And if I swap the sign on this, it's the opposite. As I go to negative, as x goes to negative infinity, the function goes to infinity and it goes the other way down. Okay, and that's no matter how big this is, because this could be x to the 20th, right? And it's still, I mean, yeah, this looks weird, but it still follows the same behavior. Okay. All right, so that's enough on that one. So let's go ahead and go to the next page. All right, I saved myself a little bit too much room here, but that's fine. So go ahead and split your page into 2. We're going to do example 6, and then we're going to go do 7 and 8, and then I'm going to make an example 9 here just to help us out for square roots, just to do at least one of those, okay? So let's do this. So here, so go ahead and split your page. That way I have room to do some other stuff. All right, so let's use algebraic limit laws to calculate the following limit. All right, so we're going to use the limit laws here instead of just saying stuff. We're actually going to calculate it directly. All right. So notice if I plug in infinity here, I'm going to have infinity over infinity. That's not going to help me whatsoever, right? But we're going to use the property that 1 over x to the n as x goes to infinity. This, so let's just say this function. As x goes to infinity, this function, no matter what the n is, right, it's going to go to 0. I'm going to use this property in order to solve these. And so what you do is you divide, right, this here, divide by the highest power in the denominator. You can take the, and so this is how you solve basically all rational. So for all rational, so polynomial over polynomial, you're going to divide by this. Let me show you what that does. So this is going to take the limit as I go to negative infinity. And so here I'm going to have the highest here is x cubed. So here I'm going to have minus 2x cubed divided by x cubed divided by 4x cubed plus 3x divided by x cubed. And so you're going to divide by that. What you're really doing is x to the n over x to the n. You're multiplying by a 1. Oops, n. You're multiplying by a 1. It's 1 over x. Oops, let me make that clear. Let me make that a little bit more clear. X to the n divided by 1 over x to the n. Okay, this is a 1, right? This is really equal to 1. Since whatever it is, it's the same on top and bottom, I'm allowed to multiply by 1. So here I'm just dividing this out. This is the same. Here we'll just go ahead and do the distribute of x implies to minus infinity. Oops, forgot the minus sign. Minus infinity of 1 minus 2. So this cancels out. Here you get 4 plus 3 over x squared. Now what happens? Well, we can go ahead and stuff the limit on the inside now. So here, this is the limit as x goes to minus infinity of minus 2 over the limit as x goes to minus 2, or oops, I said minus infinity, I wrote minus 2 of 4 plus the limit as x goes to minus infinity of 3 over x squared. Okay, so here, the limit of this is just 2. It's just minus 2, right? The limit of this is a 4, and the limit of this is 0, right? So this is 4 plus 0. So this is minus 2/4. And so that's how you solve this one directly using the limit laws. Okay, so I'll leave this up for a second. So I'll go ahead and leave this up for 1 second. Whoops. All right. How does the no? Oh, here, since I can divide, notice that. So one thing you're allowed to do is if I have a plus b over c, that's the same thing as a plus c over a plus b. Now, can you do it the other, a over c? Hi. b over c. This is fine to do. However, you cannot do the opposite. I can't have a over b plus c. That does not equal a over b plus a over c. This is not true, right? But this is okay. And so here I'm just splitting this x cubed. So x cubed divided by x cubed is just nothing, right? So I get the 4. And then here 3x over x cubed just gives me x squared. Okay. All right. And minus 2/4 looks like a negative half, but let's look at this. Let's look at this real quick. All right, so here, and notice here as I go out, it goes to this. Oh, here. So here we're using this property. How does it get to 0? F of x over anything as x goes to infinity goes to 0, okay? Over all the powers. As we go out to the end, it always goes to the powers, right? Because I'll have a really large number over 1, and that gets closer and closer to 0. And so here, this limit by this is closer and closer to 0 from last time, okay? All right, so that's how we do this problem. So let's do 2 more of these problems. Yeah, because this right here as x gets sufficiently large, this will look like 3 9,000ths, 3 1 trillionths, right, or whatever, right? And you can just reduce, and you say I can reduce to a half, minus a half. Okay. But if you gave me this on the exam, like, yeah, that's exactly what I wanted. All right, so let's do the next two. All right, so let's do this 2 more times. So the other thing we're changing here is this. They're just changing the power on the x and just show you how that operates differently. All right, so now we're going to do the same exact thing again. So we're going to divide by the highest denominator, but in this case, it's x to the 5th. So here, I'm going to take the limit as x goes to minus infinity. And here we're going to say minus 2x cubed over x to the 5th, because that's what it is this time, divided by 4x to the 5th plus 3x squared, all divided by x to the 5th. Here, so we just divide it out by this. So that's what we're doing for both top and bottom. We'll simplify. So the limit as x approaches infinity, minus infinity. So here I'm going to have minus 2 over x cubed. Make that look like a cubed. Divided by 4 plus 3. This is a squared, so this gives me 3 over x cubed. All right, so what happens here? What happens here? So here we can just go ahead and we'll know how this will go. We can stuff the limit in, but we can just go ahead and write that. This is a 0 up top, right? This is a 0 up top plus 4 plus 0. So this looks like 0. Shouldn't it be? Oh, you're correct. Thank you. This should be x squared. Right. Thank you. This is a 3. This is cubed. This is squared. All right. So let's go ahead and type this in Desmos and see if that's what we indeed get. So here, so this is now to the 5th. This is now squared. And this indeed looks like, as I get closer and closer, looks like I get closer and closer to 0. Okay. So this works out. All right, let's do it one more time. Let's do this one more time. Go ahead. So here, I guess I can't really show both at once. So here, our largest is x squared. And so here we're going to do that one more time. So we're going to take the limit as x approaches. This time we're going to go to positive infinity of minus 2 x cubed over x squared. So we always take the largest on the denominator. So that one, divided by 4x squared plus 3x divided by x squared. So this ends up equaling to minus 2x over 4 plus 3 over x.
Wouldn't it be over x cubed? Sorry.
Oh, when I'm dividing?
Yes.
Oh, no. So you take the largest in the denominator. So the largest in the denominator here is the squared. Again, how do we get all the zeros? Oh, notice that any number divided by x to any power as x goes to infinity ends up being 0. Okay? So let me just, the limit of 1 over x to the n as x goes to either positive or negative infinity, it doesn't matter which, is equal to 0. Okay? That's how you get these. So this zeroes out, this zeroes out. So you get 0, 0, so it's equal to 0. Okay? So here, we're going to use that same property. This zeroes out. And so this is equal to -2 force x, because this is 0. I guess I could, let me do that in 2 steps, I guess. Plus 0, which is just 4. So this is just -2 force x. But notice here we have -2 force x. Well, now we're going to go back to what we did on this right here. We are left as, oh, sorry. I forgot to write my limits, didn't I? I was not being very careful. This is still the limit as x goes to infinity. This is still the limit as x goes to infinity. And let me write this on another line. And this is still the limit as x goes to infinity of -2 over 4x. Well, -2 over 4x, well, x, this will go to positive infinity, but since I have a negative number here, it's going to go to negative infinity. So this should go to minus infinity. So once again, so you here is, this is odd, right? This is an odd power, 1. So this goes to positive infinity. Then I multiply by its constant, its coefficient, I say. And the coefficient's negative, so this goes to negative infinity. And we can just double check this super easily. I'll just go ahead and check this. All right, so here, what we have here is we have x squared, and then this to the first power. Oops, oh, it's going to want me to type in black one. There we go. And so we get this funny looking graph right here. Notice that as we go to positive infinity, this number is going to negative infinity. As we scroll out, look over, this is indeed going to minus infinity. Okay. All right. What's the power on the bottom of the fraction for, oh, this is just, okay. All right, so that's that. So let's do one extra problem real quick. I did want to do an extra problem. And I just wanted to show you how the book goes over it in this section. I haven't done that many square roots, so let's do a square root with you. So I'm going to go write this on page 5's notes, just because I left room for it here. And so I'm going to just write extra example real quick. So I want to find the limit as x approaches infinity of the square root of x plus 1 minus x. Okay. And so here we have some problems. So if we just plug it in directly, I'm going to get infinite minus infinity. So a direct plug-in, so if we just plugged in, I get infinity minus infinity. And so that does us no good, right? Does us absolutely no good. Oops, I'm sorry, there should be a square right here. There we go. So this gives us infinity minus infinity. That does us absolutely no good. So plugging it in doesn't work. So we're going to have to do some algebra. And so the way to do this, usually if you see square roots, is just to try to get rid of the square root. And to do that, you multiply by its conjugate. So here, and then I'm going to multiply by the square root of x squared plus 1 plus x divided by the square root of x squared plus 1 plus x. And by doing that, this is the trick you almost always use for square roots. And by doing that, let's just see what we get. Oops, I forgot my minus x, didn't I? I'm going to take this quantity and multiply it by this. So we're just going to, so this multiplied by this gives us x squared plus 1. This times this plus this times this cancel each other out. It's a difference of squares, right? And so here I'll get minus x times the square root of x plus 1, and this is going to be plus square root of x plus square root plus 1, so that cancels out. And then here I get minus x times positive x. It was minus x squared. And then on the bottom, I have the square root of x squared plus 1 plus x. All right, well, I can, oops, and I forgot something, didn't I? This, hold on. Gotta be writing it all. I've been terrible about doing it all day. We also need to type in our limit. Do not forget your limit, like I've been doing today. All right, so now let's do this. Well, this part cancels out with this part. And so what am I left with? The limit as x approaches infinity of 1 over the square root of x squared plus 1 plus x. Well, what does this go to? Well, this goes to infinity plus infinity. So this goes to infinity. And so 1 over infinity goes to 0. So this all over goes to 0. Okay. So that's our extra problem. So let's finish our limit class, our limits and stuff, by looking at a bunch of these. So I'll let you write this down, and then we'll do a bunch of them all at once to kind of finish up the infinite part of it.
Professor, could you explain that last part again? Why is the denominator go to infinity?
Oh yeah, so here, let's see if I can, let me go to the next step. So here, I can plug this, I could stuff in the limit here. If I wanted to, x goes to infinity. I mean, this just goes to 1, right? And then here, the limit as x goes to infinity. So here I have x squared plus 1 plus x. So if I'm looking at this directly, this gets infinitely large, right? The plus x gets infinitely large. This gets infinitely large. So an infinitely large number plus an infinitely large number, or it's this increases that bound, this decreases that bound. That's the correct way of saying it. So this will go to positive infinity. This goes to positive infinity. Since they both go to positive infinity, this goes to positive infinity, and 1 over infinity for limits means 0. Kind of like we had up here. As this x to the n goes to infinity, so 1 over that goes to 0. Okay. All right, so let's do the last page. Where's the last? Oh, I don't have the last page up. I export these super fast. So I have them for reference. I go ahead and replace the ones I have. I don't say bye-bye. Open up the last page of notes for this. All right, so let's look at these. So here's the last page. We're just going to use the graphs below to help us to figure out what all these limits are. You can use graphical, numerical, or even direct computation to solve any of these. So let me zoom out. So let's just start here at A. So as x squared goes to infinity, the limit of this is infinite because this is going to increase without bound. All right, so we just say infinity. Here, as x cubed. Where's my x cubed? Here's my x cubed, right? As I go to minus infinity, this is going to decrease without bound. And so we just write minus infinity. Here, or e to the x, notice here graphically, this is going to increase without bound. So we go this to infinity. And so this really just saying, what's the end behavior? The end behavior for this is positive numbers that keep increasing. The end behavior for going in the left direction is negative numbers that keep increasing. Here, it's positive numbers as you go to the right, which are ever increasing. So that's what it's saying here. And e to the x, if I go into the negative, if you notice here, this will end up being very close to 0. So it ends up coming to 0. The limit for the natural log, here's some natural logs. So we'll do a little bit of the natural logs. As I go to infinity, this actually does increase without bound. It's really slow. This one's a lot slower than either x squared or either the x or even just x to the plus 1, but it still increases without bound. And so we give this one positive infinity. Here, when I come into 0 from the right side, as I'm walking into 0 from the right side, this is going to become really, 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 really small. And it's going to become, as I get really small x's, I get closer and closer to minus infinity. Okay. And you can kind of use this a little bit as a chart to help you solve some things, right? All right, so let's look at our x, 1 over x. So here's our 1 over x graph. So if I look at 0 coming in from the right-hand side, we're going to go up to the positive infinity because I'm coming in from the right, and that's going to go up. From the left-hand side, it's going to go down to minus infinity. And as I go out to infinity, notice that this goes to 0. This will 0 out. Okay. Same thing here. If I have my 1 over x squared, as I send this to minus infinity in the x direction, it just zeroes itself out. The limit of cosine, so our cosine graph is right here. When I hit 0, well, this is just 1, right? It's just a value. This one you can plug in. Cosine of 0 is 1. I mean, it's defined there. There's nothing wrong. This is direct substitution. Now, this is important. As I take this out, as I go to infinity, cosine is just going to keep going up and down, up and down, up and down between 1 and 0, 1. So this does not exist, right? Because it doesn't settle at a number. It doesn't go up to infinity. It doesn't go down to infinity. It just doesn't exist. Okay. And then here, sine of 0 is 0. And then here we look at tangent. So tangent, if I'm coming in from the left side, to square root 2 over 2 goes up to positive infinity. And as I come in from the minus side, or hold on, if I come in from the left side, if I come in from the right side, notice it goes to negative infinity. So these are just a bunch of different limits that are useful dealing with infinities and stuff. All right.